All right, so we started section 10.3 last time, but let me remind you where we were. We'd introduced two new topics in this section, specifically combinations and permutations, though in the opposite order of that. And we talked about the fact that while they're very similar in terms of their formulas, the primary difference is whether or not the order matters. So when we're dealing with a permutation, the order of something matters. And we saw some examples of this back in section 10.1 when we looked at creating a three-person grouping of students where they all had titles, right, roles. We had president, secretary, treasurer in that example. There was another one we did that had just president and treasurer. So when we're looking at something where the order matters of how something happens, that's a permutation. And this is the formula. And we also talked about the fact that this formula could be thought of, and we will continue to think of it as the number of ways we have of choosing or from among which we choose. So the N at the beginning is the number of objects or people we choose from. The R at the end is the number we actually are going to be choosing. So the numerator is the total number of any possibilities of things. That's a factorial. And then the denominator is actually the value that we don't choose. And the example that I given is going out to eat somewhere, and we had 12 friends to choose from. We did this right here on this first one. 12 friends to choose from, and there are 9 that do not get chosen. We only choose 3 of them. So we had 12 factorial on the top. We had the 9 factorial, which is the number we didn't choose on bottom. Okay? And then we looked at combinations. The difference being in that in combinations, the order does not matter. So we did things like choosing a committee. Okay, so that was an example we did back in 10.1. We chose a committee of 2 people instead of the 2 people having specific roles. And so it didn't matter what order they were sort of put on the committee in. They had the same purpose or play in the committee. And so the difference on this formula is that we don't just divide by the number of things we don't choose. We also divide by the number of things we do choose. So again, the second example here was that we had 12 people, 12 friends or whatever, and we had 3 that were coming with us to dinner. So we divided by the 9 factorial, the 9 that we didn't choose, because their order in which we would have chosen them is irrelevant. They didn't get to come. And we divided by 3 factorial, because again, the order in which we chose the 3 people who were going with us also didn't matter. So it didn't matter in this case, so we divided by the 3 factorial. When we did this, we got a much smaller number for the second one, combinations, than we do for the first one, permutations, because the order doesn't matter. Okay, so what we're going to do next is we're going to take a look at several examples where our primary goal in the problem that we haven't done yet is to decide, does the order matter? And there are clues in the way that something is worded as to which one we're looking at, and we're just going to have to try and get better at deciphering those clues. So our first example is a contractor. Jeff Hubbard is a contractor, and he builds homes. He has 8 different home models, or like blueprints, right? And he presently has 5 lots, right? 5 pieces of property to build on. It says in how many different ways can he arrange the homes on the lots so that 5 different models will be built. Okay, so read through that again yourself and think, is this a combination? The order doesn't matter. Or is this a permutation? The order does matter. What do you think? It is a permutation. Why is it a permutation? What sort of clues you into making that choice? Okay, there are 8 models and there are 5 lots, but that's not why. Any other things in there that would sort of red flag you or make you think it's a permutation? Yes, that's it. This phrase, different ways. So if he has model A and then model B, okay, let's just do 2 of them for the purposes of discussion, and he puts model A on lot 1 and model B on lot 2, or if he switches that, that's a different way of putting them on the lots. Sometimes, and this is actually an example of one too, prior knowledge of what's going on in the context of the question will also help you to make that decision. This one actually has some of that too. So if you know a thing or two about building, and I don't mean like physically building, but sort of structuring like a neighborhood or whatever, You might also believe that this one is a permutation for a couple other reasons. Let's say the lots aren't the same size. Or maybe they are, but it's more preferable to be in the corner lot because of the way the house has to be placed. Or maybe it's less preferable. Maybe you don't want to be on the corner lot because it's a busier street that's bordering that. Are you with me? Those would be other caveats to why you might have a different sort of arrangement of your house choices. All good? So this one is a permutation. So when we write these out, we're going to start by listing how many things we have to choose from. How many options are we choosing from? 8. There's 8 floor plans or 8 models. How many are we going to choose? 5. And we have to choose 5 different models because it said so, right? There's different models of this, and we're choosing 5 different models. So 8p5 means I'm going to put 8 factorial on top. And the first number always goes on top. And then with a permutation, the only thing that goes on bottom is the number of things we don't choose. Or if you prefer to go back to this strictly, like from a formula perspective, it's a subtraction problem on bottom of the 2 values. And you'll also get 3 factorial, namely the number of models that didn't get chosen. So when we're working with factorials, we're going to write them out. 8, 7, 6, 5, 4, and then I'm going to stop at 3 factorial because the 3 factorial matches the 3 factorial on bottom. If I get to the point, and I do on all the problems, where I've got a perfectly matching factorial, right? 3 factorial, 3 factorial, they match perfectly, I'm able to cancel them out. The reason, just as a reminder that I'm able to do that is because it means I have 3, 2, 1, because that's what 3 factorial is, on the top and the bottom, okay? And I'm canceling this in the perspective of equivalent fractions, right? If a fraction, this is a fraction, has a factor in the top and a factor in the bottom, they can be divided by that factor or reduced. So in some sense, I can do this sort of one at a time. The 3's cancel, the 2's cancel, the 1's cancel. But to shortcut writing it down, we can leave it written as 3 factorial and cancel the 3 factorial out completely. So this leaves us with 8 times 7 times 6 times 5 times 4. What value does that give us? 6,720. 6,720. Okay, is that good? Okay, let's take a little bit different structuring of language and see if we can find the key items to make our decision. We have Julie, this is according to the class schedule one, who apparently has a very flexible degree because she gets 10 electives. Do any of y'all get 10 electives? That's a lot. Autumn's over here going, no, I'm an education major. Education majors get like almost none. I mean, it's crazy because everything is so scripted because of state licensure exams and so forth. So her plan apparently has a lot, though. She has 10 electives, and she decides to start by taking electives instead of starting with any of the other requirements. It says if no courses have prerequisites of one another, that's important. We got to make sure that makes sense. No prerequisites, so you can take them in any grouping that you wish. And there are 17 courses to pick from. How many different selections of 10 electives could Julie make? It is a combination. And it's not a combination just because the last one was a permutation, although you might have thought that. Why?
You were struggling to not say.
I know, I was. Do you see the phrase that I'm supposed to say here that tells me, though? What's the phrase? Okay, the no course has prerequisites is part of it. But even without that, it could still have language that would force us to do a permutation. There's something else. It's selections. A selection just means I'm going to take a grouping of them and take them. If it said how many different ways could she take her 10 electives, like it said over here, different ways, I'd actually have a permutation. Are y'all with me? Okay, so it does matter when we're talking about a selection, which just means like, think about selecting, like a dessert, a bunch of desserts. Well, it doesn't matter the order in which you select them. You're just selecting them, okay? So this one is a selection. It is a combination. So how many is she choosing from? 17. There are 17 options. And how many will she choose? 10, at least if she wants to graduate. Okay, so what goes on top? 17. And with combinations, we're going to divide both by how many we select and by how many we don't select. So how many are we going to select? 10. So how many of those electives is she not going to select? 7. Okay, so if it were a permutation, it would just have a 7. It'd just be how many we don't select. But with a combination, we get both of the pieces. Notice this denominator as well. The denominator for a combination always has 2 pieces that adds up to the numerator, right? 7 and 10, that makes my 17. Okay, so we're going to write out our 17 until we get down to 10 because it's the first one. So 17, 16, 15, 14, 13. Let me move this over so I have some more space. 12, 11, and 10 factorial. I have a 10 factorial matching, and then I have 7, 6, 5, 4, 3, 2, and 1. Okay, so cancel out the 10 factorials. Okay, so what happened last time was that we discovered that sometimes you can just multiply the top out, multiply the bottom out, divide them in your calculator, and be done. And sometimes your calculator gets too big of a number that it won't let you do that, right? We got some scientific notation showing up. Do y'all remember that? Okay. So our sort of default position is going to be to reduce things because we don't always know when that's going to happen. It's kind of a waste of time to check every single time because a lot of times it happens that we get scientific notation pulling out of this. So let's look at some things to reduce. So what do you notice on bottom that you could either pair up or individually cancel with pieces on top? Okay, so the 7, do you want to do 7 and 2?
You could, and also could use the 2.
You're going to use a 2 for something else? Sure. Okay, so we'll do the 7 and the 14 to give me a 2. What else then? 5 and 3. 5 and 3 would make the 15, right? What else?
4 goes into the 16.
Okay, 4 goes into 16 4 times. And?
And you can use the 2 and the 6.
Yeah, the 2 and the 6 would make a 12. Okay. And remember, whatever you cancel, as long as you're canceling correctly, it will give you the same answer, no matter if you cancel something different than I just did. So looking at what's left, we have 17, 4, 2, 13, and 11. So go ahead and grab a calculator and multiply 17 times 4 times 2 times 13 times 11. How many different selections could she make? A lot, right?
19,448.
Yep. Almost 20,000 different selections.
That's also assuming that electives are all at different times.
Yes, we do have some restrictions if we were actually working on a class schedule creation, but these are just selections, not actually like course schedules. It's a very good point. Okay. All good? Okay. Our next example is a really long one. In fact, it's such that it's got lots of parts. So I want to make mention that sometimes I get people frustrated because I do this really long example. The reason I do the really long example is because there are a few of them that are related to this in your homework, but there's so much setup in understanding the problem that I want to make sort of maximum use by asking you lots of questions with the same setup. Are you with me? If I have to create a new setup every single time, we can't do as many problems. So that's why this is happening. So when you get to the homework and you're like, there's only 2 questions related to cards and all these other things she didn't talk about, that's why. It's not that all of those things are uniquely different. It's just that the setups are going to look a little bit different. So this one is talking about a card game, specifically poker. But in order to talk about this, we need to talk about a deck of cards. So depending on your experiences with deck of cards, you might want to write some of these things down. We play lots of card games in our household, especially when we go to the lake, which is a place that my in-laws own with family, like extended family. So cards are very familiar to me, but they may not be familiar to you. So I'm going to run through some details about cards that you may or may not know. Okay, so a standard deck of cards, the one we're talking about, has 52 cards. We're not counting jokers. Okay? So this is not counting jokers, partly because we're playing poker, and you wouldn't have the jokers if you were playing poker. Okay? So we're not counting the jokers. Within a standard deck of cards, there are half the cards that are red and half are black. So there's 26 reds and 26 blacks. Okay? Within the deck of cards, there are 4 suits. There's hearts, they're red, so there's 13 of those. There's diamonds, also red, 13 of those. And then there's spades, which are black, and there's 13. And there's clubs that are black, and there's 13. Okay, pretty good? Okay. The cards themselves, besides having suits, those are called suits, the hearts, the diamonds, the spades, and the clubs, they have a value on them. So they either have a number, like the numbers themselves go from 2 to 10. There's no number 1 card. There's a 2 up to a 10. So every suit has a 2 through 10. Or they have a face on them, and they actually look like faces. And so there's jacks, queens, and kings. Right? Those are our face cards. So every suit has 3 face cards, jacks, queens, and kings. What have I missed? Aces. Okay, there's also a card that's an ace. An ace is not considered to be a face card or a number card, okay? It's something sort of outside the realm of those 2 descriptions. And depending on the game that you're playing, that face card will either be the high card of the game, or it could be the low card of the game. Or if you're playing some games, it can go back and forth between. Blackjack does that. You can use it either way, okay? So what we're going to be taking a look at is numbers of ways of counting different types of hands of cards. Now, ignore the fact that it's poker because that's sort of irrelevant to the next question I'm asking. But think about any card game you've ever played, be it Old Maid, Go Fish. We could do Phase 10, Rook, any of our gambling games too, like any of those games, any card game you've ever played. Somebody starts out with giving you a hand of cards. Can you picture it? You've got these cards, they've been dealt to you, and you pick up your hand of cards. What is the first thing you usually do when you pick up your hand of cards?
Look at the cards.
Look at the cards, and then what do?
Organize them.
You organize them based on whatever your game is you're playing, right? Right. So like if you're playing Old Maid and you've got the Old Maid, you're trying to put this in a place that somebody's going to pick the Old Maid out. If you're playing Phase 10 and you're at a specific phase in 10 where you're putting all the numbers together, you're going to reorganize and put all the 7s together. Right, things like that. So depending on the game that you're playing depends on what you do to organize your cards. So, does the order in which the cards were dealt matter? No. Because what's the first thing you just did? You reorganized the cards. Everybody good? Okay, so what that tells us is that anytime we're looking at a card game question, what are we using? Permutations or combinations? We're using combinations. Okay, everybody good with that? So every question that's left in section 10.3 is going to be a combination question because it's all going to relate back to our deck of cards. All good. Okay, one more thing to be aware of. There are some questions in sort of the test bank inside of my math lab where they do create hands of cards. They're not 5-card hands of cards. So just pay attention to the question that you're asked. There are some that show up and they create some other kind of a game where you don't get 5 cards, you get 6 cards. Or 7 cards, or 4 cards, okay? So just pay attention to that. So the question that we're asked to do is to consider a 5-card poker hand specifically. Has anybody ever seen the Poker Channel? No? My husband used to watch the Poker Channel all the time when we lived in Ohio. I don't really know why, but that was something he watched. And on the Poker Channel, there's like a thing in the bottom corner that tells you the percentage chance when somebody gets dealt a certain card that they're going to win, okay? So those percentage chances are based on what we're actually going to be doing in this section. They're based on combinations. At any rate, so we've got a 5-card hand that's been dealt to us. Do you remember how many cards I said was in the deck to begin with? 52. So there are 52 cards I'm working with combinations, and I'm supposed to be dealt a hand of 5. So I have 52 cards, and I get 5 of them. Everybody good? Okay. So combinations and permutations both put that 52 factorial on top. And then with combinations, I have 2 pieces in the bottom. One piece in the bottom is how many cards I choose. That's 5. And the other piece is how many I don't get dealt. How many cards are not dealt to me? 47. And once again, notice 47 and 5 add to the 52 on top. Everybody good? Okay. This is definitely too big of a number for your calculator to work with. You try and do 52 down to 1, and there's no way your calculator is going to do that and be exact. So we're going to write our 52 out until we get to 47 factorial. So 52, 51, 50, 49, 48. I'm run out of space. Let me shift it a little bit. And 47 factorial. Over the same 47 factorial. And then 5, 4, 3, 2, and 1. Okay, so far so good? What's the first thing you're probably going to cancel? Yeah, 47 factorial. Now, this numerator and this denominator are far enough apart, we're probably not going to be able to pair things up and just find cancellations that are perfect. So let's just go through the denominator and reduce from left to right. What will the 5 divide into? The 50. So that'll give me a 10. How about the 4? 48. That's one option anyway. So 48 divided by 4 is 12. Good. How about my 3? 3 will go into 51. It'll also go into 12, so you can pick your favorite. What is 51 divided by 3? 17. Now, some of you were like, how do you know 51 is divisible by 3? Do you know, Josh, how you can just look at it and tell? Or were you just sort of supposing? Do you know?
I just do it because I just divide it to where I can. I do 3 times whatever I know, like 10,
Okay.
30, and the ranger's 21. I know that's divisible by 3.
Okay, do you guys want to know a quick trick to know?
Yeah.
Okay. What's 5 plus 1?
6.
Is 6 divisible by 3? 51 will be as well. And it always works.
23.
Always works. Okay? So you can take any, it doesn't have to just be a 2-digit number. You could take any number as a digits. So if you had the number of 5,423, you could add 5, 4, 2, 3. I think those are the numbers I just said. And if the numbers sum would be divisible by 3, then the original number would be 2. Cool trick, right? Not only does it work for 3s, but it works for 9s. It doesn't work for any other numbers. So don't go doing that for 8s or something. But it works for 3s and 9s. Okay, so it is going to be divisible into the 51. It does give us a 17. How about the number 2? We have lots of options. What do you want to divide the 2 into? 50. Okay, so the 50 is not 50 anymore. It's a 10. So I'll divide it into the 10, which leaves me with a 5. Sound good? You could do it with the 52 or with the 12 as well if you wish. All right, so remember, no matter how you decided to separate them out and do the division, you'll get the same answer if you've done the division properly. I have a 52, a 17, a 5, a 49, and a 12. What do you get if you multiply those values together?
2,598,960.
It's almost 2.6 million, right? Different hands of cards. That's why you can play the game over and over and over again, and the outcomes never are the same. Right? There's 2,598,960 different 5-card hands of cards. It's a lot. Okay, so we're going to narrow our focus a little bit as we go. Some of these questions are specifically types of card hands that mean something in this particular game, and some are not. The next one is one that is not. It's just a hand that's all red. Okay, so you get a hand and it's all red. Fun fact, we played Rook when I was a child. My dad really liked Rook. And there was one time when we were in the middle of playing a game of Rook, and I got up to get something from the kitchen or use the restroom or something like that, and came back, and he dealt his hand the hands of cards. And with Rook, you have 4 different colors of cards, kind of like the 4 suits. And my entire hand was the same color. Now, in Rook, that means that it's the same suit. Okay, so it'd be like getting the entire hand of cards, and it would be 13 cards if we were playing with poker. 13 cards, if you will, that were all diamonds. Rook's a lot like spades. Have you played spades before? That's another one that's just like rook, really. Okay, that doesn't happen. You're never going to get dealt the entire hand. In the rook game, it was yellow. My dad fixed the hands just to see what I would do because he was trying to mess with me. In this one, all reds is not that super special, and it doesn't really mean a whole lot. But how many red cards are there? There's 26. But how many am I going to be choosing to fill up my hand? Just still 5. So this one's 26C5. Whoops. All right, so combinations, right? So I'm going to do 26 factorial on top, and I'm choosing 5. So how many am I not choosing? 21. So I'll write my 26 down to 21. I have my 21 factorial on bottom, and then I have the same 5, 4, 3, 2, and 1 from the previous problem. And I'll cancel my 21 factorials. Okay. Same song, second verse. Now, you might be sitting here and thinking, okay, well, we just halved the deck, so it should be maybe like, maybe about 1 million different answers when I get to this, okay? Like that seems sort of like an intuitive, like I might think that there's about half as many options. So we'll check that theory when we get there. What will the 5 reduce by, or reduce into? The 25, giving me 5. How about the 4? 4 with 24 will work, giving me, 6. I was thinking about my next piece that I was going to do. 6. Yeah, in fact, we could actually do the 3 times 2 is equal to 6 and cancel it completely if we wanted, right? Or we can do it in steps. I can look for the 3, divide it, and I can look for the 2 and divide it. So we're going to have 26, 5, 23, and 22. Okay, so 65,000 is a lot, but it is nowhere near a million, which would have been half of the previous answer, right? Nowhere near. So you half the deck and you significantly change the number of hands, not just by half, but by a lot more than half, right? A lot more than half. So 65,780 different hands. Okay, you ready for another one? We're narrowing it down a bit more. Now we're not just having red, we're specifically having all hearts. This one actually has meaning in poker. Do you know what a hand is when it's all the same suit?
Flush.
It's a flush. So if you hear somebody talk about a flush, that's this kind of hand. Specifically, you might hear somebody call it something a royal flush. Royal flush actually means that it's the top 5 cards in that suit. So it would actually go from ace down, the top 5 cards. So ace, king, queen, jack, and 10 would be a royal flush in a specific suit. This one's just a plain flush, hand of hearts. How many hearts are there? 13. How many am I choosing? 5. So 13 factorial on top. I'm choosing 5. How many am I not choosing? 8. So we're going to write our 13 down to 8. And we're going to have, our 5, 4, 3, 2, and 1. So cancel our 8. These numbers are close enough together, we might be able to do some pairings and work things out nicely. What pairing of numbers on bottom would work nicely with the top?
3 and 4.
3 and 4 make 12. 5 and 2 make 10. So this one leaves me with 13, 11, and 9. 1,287. Okay, again, 1,287 is a lot of hands, but it's nothing compared to 2.5 million, 2.6 million almost, right? Absolutely nothing. Now, that's not all of the hands that are called flush hands. That's just all of the heart flush hands. You'd also have 1287 that are clubs flushes, right? And 1287 that are the spades flushes and 1287 that are hearts flushes. So we'd have 1287 times 4 if we wanted to know how many flush hands there really are total. But for hearts, this is 1287. How about D? All jacks. So what's that mean, Samuel?
You can't have
Okay, say that louder.
you can't have
You can't have a hand of all jacks. Why?
there's only 4 of them.
There's only 4 of them. So if you have a hand of all jacks, you're cheating. Yeah? Or you're playing with more than one deck, which is not what we started our problem with, right? And you could be playing with more than one deck depending on how that was working for you. But yeah, a hand of all jacks doesn't happen. So how many ways can you get a hand of all jacks? 0. And I make mention of it because, again, inside of the test bank, inside of my math lab, and you may or may not get the same question, right? There are some where it's not possible to get the description that they give you. So just pay attention and be aware that 0 is an option. It could be something that's just impossible. This is impossible with the constraints of our problem. Let's say, though, that they didn't give you one where you had a 5-card hand, you had a 4-card hand. Could you have done it then? Sure. Okay, so pay attention to the constraints of the problem. Okay, but what if you had 4 jacks and you had something else with it? Right? So now you don't just have 5 jacks, which is not possible. This is possible, right? Do you know what this kind of a hand is called? 4 of a kind. Right? It's not common. Now, it's not the only 4 of a kind hand. You've got a 4 of a kind jack's hand, you've got a 4 of a kind seven's hand, and a 4 of a kind ace's hand. So there's 4 of a kind of lots of different kinds, but it is one of the 4 of a kinds. Okay, everybody good? Okay, so we're going to start the way, Stanley, that you were starting your last problem until you realized that it wasn't going to work. What did you say first? You don't even remember. I remember you saying 4C4. Does that sound familiar? Okay, so there are 4 jacks, and I'm going to choose all 4 of them. Make sense? But that does not complete my hand. I need 5 cards. So what am I going to do for the last card? Well, I'm going to choose one more card from among how many are left? 48. And what you see happening is embedded inside of this combination is there's a fundamental principle of counting. I have the number of ways of getting 4 jacks, and then I have the number of ways of getting one of something else, and I'm multiplying those results together. Just like the shirts and the pants and the shoes last time. Remember that? This is the same thing that's happening, but with a slightly different context. So we're going to do 2 different combination descriptions. First one is going to have 4 factorial on top, and I'm choosing 4 of them, which means how many am I not choosing? None. This is a 0 factorial. I mentioned last time that we defined 0 factorial to be what? Do you remember? It's 1, and part of the reason why is for this very purpose. I need it to be the number 1 in some ways, because the formula wouldn't work if it were anything else. Now, that's not really the reason why, but you can just see here why it needs to be that way, right? It needs to be a 1. There should be only one way of getting all 4 jacks. They're all 4 dealt to me. That's one way, because it doesn't matter the order in which they come, right? So if the order doesn't matter which they don't, then I actually still just have one way of getting 4 jacks. And then I have 48 cards left over, so it's 48, and I'm choosing one of them. How many am I not choosing? 47. So that's my other piece of my denominator. Now, the first one, I don't have to write anything out. What do you notice happens on the 4 factorial over 0 factorial 4 factorial? The 4 factorials already cancel. So what is that whole fraction going to equal? 1, right? I have exactly the same value on top as I have on bottom. When we divide a number by itself, we get back 1. So this piece right here, all of this together is the number 1. The next piece is 48 times 47 factorial. And then I've got my 47 factorial down here to cancel with my 1. So my 47 factorials cancel. And what am I left with in total? 48. So this is 1 times 48 or 48. Now, just think about it logically for a moment. How many 4-card jack hands would I have? Well, I have 4 jacks and a 2 of diamonds. And I have 4 jacks and a 2 of spades. And I have 4 jacks and a 2 of hearts. And I have 4 jacks and a 2 of clubs. And then I have 4 jacks and a 3 of hearts. And a 4 jacks and a 3 of diamonds. And a 4 jacks and a 3 of clubs. And a 4 jacks and a 3 of spades. And I can take all 48 of those cards one at a time and put them with my 4 jacks. And I would create 48 different hands of cards, right? Should make sense that this is 48. Does it? Okay, good. We have a couple of more. This one just says 4 of a kind. Why does it say 4 of a kind? I mean, we just said that this last one was a 4 of a kind. What's different about F than E? It doesn't define what card, right? So it could be 4 jacks, like we just did, or it could be 4 sevens, or it could be 4 kings, or it could be 4 fours. It has to be 4 of something, but it doesn't specify what. So the ending part that I'm going to write down is going to look just like what I just did, 4C4 times 48C1. All right, it's going to have that in it. But the first thing I have to do is I have to choose which of my 13 different value cards, because there's 13 options, that I have 4 of. So I need to have a 13C1 at the beginning, not because it's choosing a specific card, but because this chooses which value that my hand of 4 is going to be. Now, think about this. What was our number? 48, right? 48. There are 48 hands that are 4 jacks. How many hands are going to be 4 sevens? 48. How many hands are going to be 4 kings? 48. How many are going to be 4 threes? 48. There's going to be 48, all of them. So I'm simply going to be taking 48 and 48 and 48 a whole bunch of times. How many times? 13, because there's 13 of them. Now we're going to actually write it out so you can see that that's what happens, but that is what's happening here. I'm going to get 13 out of this guy at the beginning because there are 13 ways that I could have chosen that value card. I'm going to get the same 48 at the end. So this one at the beginning is 13 factorial over 1 factorial, that's what I chose, and 12 that I didn't. And then I have the same from the rest, 4 factorial over 0 factorial, 4 factorial, and 48 factorial over 47 factorial, 1 factorial. I'm not going to repeat the pieces at the end. We already did that. This is the number 1 and this is the number 48. But we'll write out the first one just so that we can see it really is going to be 13. So this is 13 times 12 factorial over 12 factorial times 1. The 12 factorials cancel, and there's your 13, right? It's the 13 we said we should have been getting. So we end up with something that I don't have space to write down. That's what we end up with. Let's make it smaller. All right. It's not ideal, but that's okay. So I have 13 times 1 times 48, which gives me what? 624. So there are 624 hands that are 4 of a kind. It's not very common. And so you might be saying, like, how do they make the decision? You know, it might be saying that I should point out. How do they make the decision about which hand is beating which hand? Well, one of the ways to make that decision is to simply count how many of those types of hands there are. 4 of a kind, there's only 624 of those. Whereas when we talked about our flush over here, there's 1287 of each suit. So there's like almost 5,000 of those. So 4 of a kind is less common than a flush. So if I have a 4 of a kind and you have a flush, I win, right? But a 4 of a kind of jacks is equally likely as a 4 of a kind of sevens. So there's structure put upon it from the outside that says, okay, so when you have a tied hand like that, the higher value is going to be the winner. That's an arbitrary assignment that we make within the game. But the ingrained assignment within there is how likely something is to happen. So there's two different things going on. Okay, we have a couple more left. Full house. Do you know what a full house is?
3 of a kind and a pair.
Okay, so we have 3 of one type of a card and 2 of another type of a card. By the way, a lot of this language mirrors a dice game that you may or may not have seen before called Yahtzee. Yahtzee has these same descriptions in them. So a full house hand means 3 of one kind and 2 of another. So if I have 3 of one kind and 2 of another, the first thing you need to know is that the 3 of the one kind and the 2 of the other can't be the same card, right? I can't have 3 7s and then 2 more 7s. I'd have 5 7s and I don't have 5 7s. So they have to be of different values, right? So that sort of is ingrained upon it. It has to be of different values. So I need 3 of one card. Well, by card, I mean value card. There are 4 value cards from which I need 3, and then there are 4 value cards from which I need 2. And notice I put a space in between here, and that's purposeful. Because I wasn't told what value cards I had. So I have to make that choice too. It comes back to what we did over here when we did the 13C1. I'm not choosing a card when I did 13C1, but I do need to know which value I'm choosing. Okay? So over here, I need to do a 13C1 at the beginning because that picks the value, and then once I pick the value, I choose 3 of those 4 cards of that number or face or whatever. But then I don't have 13 value cards left to pick from. I already picked one. So after that, I have 12 cards left to pick a value from. Whichever one I picked first is no longer eligible to apply, right? Pick something else. And then I pick 2 of those 4 cards. And once again, you see the fundamental principle of counting embedded inside of this problem because I'm multiplying ways of doing things together, just like the shirts, the pants, and the shoes. Now we've done the 13C1, but I'll write them out. So this is 13 factorial over 1 factorial, did not choose 12. The next one is 4 factorial over, I chose 3, I didn't choose 1. 12 factorial over choosing 1 and not choosing 11. And then 4 factorial over choosing 2 and not choosing 2. Okay, are we good? We'll write them all out, though we've done one of them before. So this first one would be 13 times 12 factorial over 12 factorial times 1. The next one would be 4 times 3 factorial over 3 factorial times 1. 12 times 11 factorial over 11 factorial times 1. And then 4 times 3 times 2 factorial over 2 factorial times 2 times 1. Lots of things canceling. So my 12s here cancel. That leaves me with 13. My 3s here cancel. That leaves me with 4. My 11s here cancel. That leaves me with 12. My 2 factorials here cancel. I still have a 2 on bottom. So the 2 on bottom can cancel with the 4, leaving me with a 2. 2 times 3 on top is going to give me a 6. So 13 times 4 times 12 times 6. Yep. Okay, so there are more of these than 4 of a kind, right? So this hand is not going to win if somebody else has 4 of a kind. But there's still not very many of them compared to the 2.6 million almost that we have, right? This is still rare. It's just not as rare as my 4 of a kind. It is more rare than having a flush, though. Remember when we did a flush, we only did the heart flush. So if we'd multiplied by 4 to figure out how many total flushes we had, we'd have more of them than this one. So this one would be a better poker hand than the flush hand would. Okay, the last example I have is arbitrary, just to show another example of how you do the counting strategies. It's not a good hand. It's just a very random kind of hand. The last one has 2 black cards, 2 diamonds, and a heart. Very random, okay? So black cards. How many black cards did I say there were? 26. So there's 26 cards, and I'm going to choose 2 of them. Fundamental principle of counting. Next object says 2 diamonds. There are 13 diamonds, and I'm going to choose 2 of them. And then there's 1 heart. 13 hearts, and I choose 1. This is a very random sort of hand, but very typical. So I have 26 factorial. I choose 2. I don't choose 24. 13 factorial. I choose 2. I don't choose 11. And then 13 factorial. I choose 1 and I don't choose 12. So we'll write a few terms out to cancel some things. I have 26 times 25 times 24 factorial. There's my 24 factorial and my 2. So the 24s will cancel. And then my, that's 2 times 1 if you prefer, but whatever. My 2 will cancel with my 26. So the 2 and the 26 will give me a 13 up here. In the middle, I have 13 times 12 times 11 factorial. So that's canceling my 11 factorial, and then 2 and 1. So my 11 factorials cancel, and the 2 reduces with the 12 to give me 6. And then 13 times 12 factorial, where my 12 factorials will simply cancel, times my 1, leaving me with 13. Okay, so let's see. I'm left with 13 and 25, 13 and 6, and then another 13. Lots of 13s. So what do you get when you multiply these results together?
329,550.
Okay, so like it's not 2.5 million, but it's the biggest thing we've had since we started, right? This is a super random hand. It's nothing special.